Hey, who's all here right now? We got Ditto and Clayton here. Let's wake up Mewbot and let's get started on some activity. There, Mewbot is waking back up. Good to see you here, Ditto and Clayton. It's a little bit cold in Texas today. So just relaxing right here. Hair's going all crazy as per usual, but we got this. We're going to start up some activity here, so let's get started on it. Here we go. Jacob, good to see you in the chat. Let's throw out some points as per usual. 100 points in the chat as everyone's saying hello. Trevor, good to see you. Oh, we got a bunch of people here. What? Let's throw out 500 points. Oh my gosh. It's a party at Stat to 1. Everyone's here. Made the text too small. Whoops, whoops, whoops. We're not knitting this, so if we break that, it's not the end of the world. Be careful, careful. Happy Halloween weekend. I know, right? I wanna dress up, go up, have some fun. All that great stuff. Trevor, good to see you. We got so many people here. Love it. We're going to use the launch data set right here. A small portion from the Kaggle competition. That's a competition site where you can win money. No joke. Like, no jokes today. There will be. We have 652 products from 2013. This is the one we're currently doing. I want to make sure this is the right activity. Activity 8, right? Tell me if you're like, hey, Brian, you're doing the wrong activity. But we have right here that we're going to use, we focused on the first. Yeah, I was like, I'm getting deja vu, everyone. I'm getting deja vu. Not that I've ever done these activities before. We saw the assumptions looked reasonable for some of them. And we have the following code right here. So what does this code do right here? Well, first off, we're loading in the launch data set. You have to make sure you have library reg class running. It's going to be up top, but I'm going to put it right here. If you have library reg class running, you can load the launch data set. This is not an Excel file. This is a data file that is inside the reg class library. So a lot of people sometimes think that, especially when it comes to midterms, a lot of people do like data 1 inside of here, but data 1 was created for you. Don't worry. I see it a lot where people do data 1. If you want to load data elsewise, you might do something like data store into read.csv. And if you have a file on your computer, like I have the Nestle's files right here, notice how it loads that in. That is reading a CSV file, and that has read in the data from you right there. We're not loading in data like that, but please note that the data function loads data sets that you have access to. So it loads specific data sets you have access to, and you can see what data sets you can load by doing this. So fires, there we go. We could go back to here and load fires like this, which is in the best GLM. You might not have that, but now fires is loading in. You probably don't have that, but there's the fires data set. So this loads data you have access to. Just want to make sure you know what the function you're using is doing. And then next, we are taking the launch data set, which we have here. Let's just clear everything out so we only see what we want. We're taking the launch data set, which we have right here, and we're only taking the first 6 whats. Take a second. I need your help right here. Hopefully this code makes sense. Help me out. We're taking the first 6 whats. Because this is the what space. And then the comma denotes the next sort of space. R reads through spaces, and when we know, oh, we're just going inside of it. Going to positions and only taking all the rows and what right here. So you could just take everything. Let's just take it all. Take everything. That's everything. We don't want to do that, though. We could just take the first row. That's the first row. You see it has 1 observation. And I kind of just have a big space to work with right here. So what am I taking? So what are we taking? We could do it a long way. There's a long way of doing it. There's the long way. Gets us the same answer. You can also see what you're creating right here, just to better look at it. Nice job, Laney, right there. Let's make Laney a mod. Laney, great work. Earning everyone another 100 points. Taking the first 6 columns right here. If you're taking like a vector of columns, like 1 through 6, you could just put 1 through 6 like we have, but you can always concatenate and choose certain things. It might make more sense to concatenate if you're going to take like column 11. Notice how the first column we took was column 11 there. We're not doing that today, though. We're just taking row or columns 1 through 6. I like to put some spaces sometimes so people can see we have a row space right here, and we have a column space over here. Let's continue on. Laney, excellent work right there. Great job. Question 1, fit the predicted model from all 5 predictors. So we need to know a little shorthand right here to get all predictors built in. I like to end my chunks right next to the code. This is the add chunk button. Make sure you know that the chunks are where code is run. You get this little nice running the code button here. And so when we fit a model, right now we're fitting linear models. We're going to store it into an object. We usually call it M for model. If you really want, you could call it model. I don't know how to spell. And so now we're storing LM, and we are going to predict profit from all 5 variables. All 5 variables right here. We're going to take profit from all the variables. This is tilde dot. Tilde dot takes all the x variables, so we have the y variable of interest and all x variables being included. Dot is like a computer way of saying like everything, or like almost like a star when you do certain types of languages. But we're going to go right here and take from, no, my favorite survey ever. Take from the PL dataset, which is the dataset we're using right here. We're taking this dataset using the y variable profit and all the x variables. So very important to know this format right here. This is the code to take all the x variables. Now we've got some important metrics right here that we need to look at, and we're going to be looking at the R squared adjusted, and the RMSE. Now we need to know what these mean. Oh, I called it model. Let's fix that. There we go. You can call it whatever you want. Just realize that that's a placeholder for what you're using to call it, whether you call it model or M, rock. It doesn't matter. Just make sure to be consistent in what you call it. So now that we have this written, I'm going to drop this here in the chat just in case anyone needs it. So here, let's drop it. We'll drop a few of these in the chat right here. And please, please, please ask questions if you have it. If you're watching along, following along right now, ask a question. Be like, what does this mean? What are you getting right now on the screen? What we have on the screen right now is the summary, which is showing us, first off, the model was built from Y. We're predicting profit using all the X variables with the data set coming from the PL data set. Here's the residuals, which actually look kind of decent. There's some symmetry among them. This is the 25th percentile residuals to the 75th. That's the 50th percentile. There's a little bit of symmetry. We see right here also that the min and the max don't appear to be outliers, which is also good. So they're more symmetric. We don't have extreme residual values. We like that. Now we're looking at the individual x's, and every single x is statistically significant, which is awesome, which means that each x brings with it new information to the model. That's how you're statistically significant in a multiple model. We have here the estimates of the coefficients and also the uncertainty for the estimates of the coefficient for the model. The most statistically significant would be x4, which brings kind of, it's doing the most work for the model kind of, or doing the most unique information bringing, because it has the highest t statistic in absolute value. No one cares about the intercept. The intercept is just when all x's are equal to 0. So some good x's. Here we are with the R squared right here. R squared tells us 68.9% of the variation in profit is explained by the variation in this model, by the x's in our model. And we have 68.66. It's kind of, and there's no clear interpretation of this, but it's our R squared penalized, and that's actually really good. The closer these two metrics are to each other, the better they are. R squared adjusted can be negative. R squared adjusted can be negative. It's just R squared with a penalty. This is not the formula for it, but literally it's just R squared minus penalty. So unless R squared is 1, that's the only instance when they would be equal. Unless R squared is 1, R squared adjusted will always be lower. There's just the rare instance when R squared is 1, and then there's no penalty because it's got a perfect R squared, so you win. Probably some problems though. So the multiple R squared is the percent of variation in Y explained by the variation in X. Once again, 68.9% of the variation in profit is explained by the variables in the model. And the adjusted R squared is a kind of more penalized way of looking at it to say, we've got a bunch of X's, but truthfully, since they're close, we're good. And last but not least, we have the RMSE, and we're predicting profit. Our model typically misses profit by about 0.2878 units of profit, whatever the units of profit are. Does it say? Misses typically profit, hard-coded. And so we typically miss predicting profit by about 0.287. And this is in units of Y. This is not a percent. A lot of times people will put percent on that. It's not a percent. It's in units of Y. So there's all of our interpretations right there. But now we want to predict, and this is a helpful code right here. We want to predict, be careful. We want to predict, I think it said, from all 5 predictors. We just did that right there. So now let's go right here and run the next bit. Here, we'll put a break in it. Question number 2, when I mock the video. How's everyone doing today? Everyone having a good Friday? It's Halloween weekend. Halloween weekend. Time to relax. Might go on a Pokemon walk after this. Been working away. Hope you're having a great weekend. We'll do some question number 2. Let's take a look right here. Interactions play a key role in many problems. Relationships are complex, and the strength of the relationship between, say, Y and X is not constant. Thank you, Peyton, right there. Doing pretty well today. Doing pretty well. But depends on the value of a third variable. And think about this. Let me ask you this. You're going to have dinner tonight. Would you like bacon on it? What if I told you you're having... See, the problem is, if you like bacon like I like bacon, bacon makes pretty much everything better. What if I told you for dinner you're having ice cream? You'd be like, hold the bacon, hold the bacon. Because in that instance, bacon doesn't make everything better. What have I told you? I'm thinking of a dinner item, though. Like pizza with bacon. Come on, it's good. So bacon would interact with things differently. So we have to ask, does the way in which y get explained by x depend on another x variable? We're going to look at the interaction term right here. So let's make an interaction model right here. And so for this one, we're going to do, is it all the interactions? Find all two-way interactions. Let's do it. So the code for this is profit tilde dot raised to second. And now we have all the interactions for the model. It should be fine. What's it mad about? No, it's not mad about anything. Here's every single interaction. Whew, that's a lot of output right there. It's a lot of output. Notice that we have things that don't have statistical significance. And I think I want to explain interactions a little more depth right here because this is our first time really talking about interactions in depth. We almost got it to the end of our lecture, but I didn't want to throw it on there and didn't want to go through it too quickly. So let me give you an example here with a much smaller example with interactions. Let's have height explained by weight and the interaction with someone's gender. Okay. Now, this is a variable we haven't used yet. This is a different model than what we're currently doing, but I want to use this right here to talk about the topic for just a moment of what are interactions. Let's take a look at this right here. Oh, there's no interaction, is there? Let's explain GPA. We need to find a good interaction. Well, I know of one that I could use. Oh, let's do this. Desired weight. Now we got quantitatives. Well, oh, the interaction is significant? Well, I'll be. We actually lucked out. We got a significant interaction right here. Let's take a look at it. Let's rerun the code and see what we got right here. Okay. So I'm actually shocked that the interaction is statistically significant. You can see the p-value for the interaction being statistically significant here. It's not as strong. Why do you square it? Oh, good question right there. So this creates all the interaction terms. So Lainey, the way this code works, sorry, Lainey, I just saw that. The reason that we square it is it does the interaction between all the variables. So the way it would be read is you're taking all of your x's and doing all the interactions. Does that make sense, Lainey? Thank you for asking. And please, please, please put those questions in the chat like you just did right there. 100 points, Lainey. This says take all your x's, and then the squaring, although it's like we're not actually squaring it, creates an interaction variable between every single x. So I have more x's down here than I would want. But if you just wanted to look like the interaction between x1 and x2, I can't type x's. If you wanted to do x1 and x2 right here, you could do this, and notice how we get the interaction. So this is the interaction term. Does that make sense here, Lainey? That this says, give me a model explaining profit with x1, x2, and then it carries through their interaction. This is the interaction term. And maybe going with the theme of the problem, it might be easiest to see this. Let's only use what's in the problem right here. Lainey, thank you so much for those great questions. Let's visualize just this current model, and then we'll go to a bigger model. Oh, that's not a strong interaction. It's a little stronger. Let me look at the big model and see the best interactions. We want to look at a really strong interaction right here. We're going to find one of the strongest interactions. Let me ask you, how could I find out which interactions are probably among the strongest right here? How could I find out which interactions, like if you look right here, I see one, which are maybe some of the strongest that bring some of the newest and like most valuable information that the other things are not accounting for. Which one right here looks to be the strongest or most statistically significant, let's say. And most statistically significant, we're going for p-value. So the x2, x5 interaction is very statistically significant. So I'm just going to focus in on that for a moment. This is not exactly what we're doing, but I'm going to make a model with just the interaction and the regular terms. So let's take a look at this model. Aha. Now I want you to think what's going on right here. I want you to tell me the way in which x5 explains profit. Be very careful. Does x5, and this is what interactions are going to do, does x5 have a positive or negative impact on profit? Does x5 have a positive or negative impact? Like, look at the lines. So take a moment right here. This is the big thing to learn about interactions. Does x5 have a positive or negative interaction on profit? What do you think? Is x5 positive or negative? And this is what interactions do. So if you get what interactions are, you'll understand how we're going to interpret this here in a second. And we'll look at some more interactions. It is negative here. So Peyton, you're half right, but are you totally right? Peyton, you're on the right track, 100 points. Keep it up. You're on the right track with it. Because there's an interaction term, well, these wouldn't be medians. This is a line predicting profit based on x5. And then we have what are called implicit lines right here where we solve out when x2 is small, which is, I believe, the 5th percentile of x2. This is the 50th percentile of x2, so it's like the 50th percentile of values, and we solve out and make a line right here. And this is the 95th percentile of x2. So the relationship x5 has with profit is what? The answer is up here. Is it negative? Is it positive? Is it slightly negative? The relationship x5 has with profit is what? The relationship x5 has with profit because of the interaction, what? I'll give it a second. I'll give it a little bit longer. The key thing to notice about the way in which x5 explains profit, what word am I looking for? It would what right now? This is the thing you must know about interactions. If there's an interaction right here, if x5 has an interaction with another variable, the way in which x5 explains profit would what on this? Because if x2 is small, x5 has a positive slope. If x2 is large, x5 has a negative slope. So the way in which x5 explains profit would what on x2? And let me repeat that. If x2 is small, then x5 is going to have a positive slope. If x2 is large, then x5 is going to have a negative slope. The way in which x5 explains profit would what on x2? Think of a D word right there. It would depend. Does that make sense? The way in which x5 explains profit depends on x2. In instances when x2 is small, x5 has a positive relationship. In instances when x5 is larger, it actually goes to a negative relationship. x5's way of explaining profit would depend on the value of x2 due to the interaction variable in the model. And so we have a simpler model here that's much easier to look at, but we can also build the much larger model. And let's look at that much, much, much larger model. x5 is dependent on x2 to explain profit. Exactly. The way in which, and also x2 depends on x5. Yep. So the way in which x5 explains profit depends on x2, and that's how we interpret interactions. This model wants every single interaction, though. So we're just going to go here and add in our raised to second. And now we have all the interactions, and we're going to actually view them right here, I think. Do we view them? Let's go to interactions. We should have C interactions, I think it is. C interactions. And let's see our interactions. Too large. Too large. We have to make it bigger. Oh, it's mad. Oh, really? 2 seconds. I have to reset R if this happens. If you get the palette error, I think it's because I'm doing a bunch of ggplots in the background or something, and it's mad about my palettes. So I'm resetting R right here as we currently do this. And I'm just going to rerun all my code, and it should work because R was mad about my plots. Ooh, did it just take all my code? Let's go back down to where we were. And we were doing the interactions. So let's recode our interaction model here. Uncomment this out. And we have profit. There's the code right there. Profit tilde dot raised to second. And C interactions. M dot int. Too large. It really wants a lot of room today, doesn't it? No way. Are you? No. Something seems a little odd here. Will the visualizer do it? Something is just going crazy today. C interactions, many equals true. I think we need the many equal true. There we go. For this code, you have to hit enter. Here's how x1 and x2 have an interaction. Here's x1 and x3. They have a very weaker. And x1, x5, x2, x3. That's a little bit stronger. When would an interaction be very strong? Great question right here. When would an interaction be a lot stronger? Remember that x2, x5 we saw earlier? When are interactions stronger? Very good theoretical question. When are interactions stronger? What do you generally see for strong interactions? Like if the way one variable explains another would heavily depend. So if we were to change one value, what would start happening to these lines for strong interactions? When there's a strong interactions, the implicit lines will be more what? When the interactions are weaker, the implicit lines will be more what? So for strong interactions, you generally see this. But for weaker interactions, you generally see this. Because look at how x3 explains profit. It's like this, it's like this, it's like this. It's like always this, it's just always the same slope for x3. It's very consistent no matter the value of x4. Like x3 really explains it the same way, independent of x4. But over here, the way in which x2 explains profit depends a lot on x5. And it's got the different lines right here drawn for you. So the stronger the interaction, the more what the lines. The weaker the interaction, the more what the lines. Great theory to know. The stronger the interactions, the more what the lines. Different slope. Exactly. So if the slopes are similar, when the slopes are similar, weaker interactions, because it's the same relationship. Does that make sense, Peyton, right there? Like x3 right here has the same relationship no matter what x4 is. There are differences among these lines, but these are just differences in x4. But the way in which x3, which is the slope of the line, explains profit isn't changing dependent on x4. But over here on this graphic right here, the way in which x2 explains profit is heavily dependent on x5. For values of x5 that are small, x2 has a positive relationship. For values of x5 that are large, x2 has a negative relationship. If you have to explain something like this on the test or for your homework, make sure to look at the graphic and then use it like we're doing here. I'll say it one more time. When x5 is very small, that's that line right there, x2 actually has a positive relationship with profit. When x5 is very large, then x2 actually has a negative and very strong negative relationship with profit. So we can see as x5 increases, the impact of x2 goes from positive to negative. So it starts here, but as x5 gets bigger, it's going to go from positive to negative. Probably one of the hardest things for people to interpret in this class is interactions, and just practicing right here with it is great. Oh, we can look through the rest of the interaction plots, but it's just more kind of strong or weak ones, but I think we've seen the strongest and the weakest. We've done that. Well, we talked about, do we need to? Let's do this. Here's our new model, and we have a lot more variables in this model, so we're probably going to see more of a difference in the r squared and r squared adjusted. Not that far. Probably going to be, definitely we're going to be looking at it. We're going to be looking at the grades and getting everything finalized by the end of the weekend at the latest, but getting everything finalized. So stay tuned. More announcements to that on come. So stay tuned, Peyton. I'm going to be grading our portion of the response questions here soon. Got to go ahead and grade some questions. Woo! So right here, we have the r squared adjusted, RMSE. And so with this right here, r squared is 72.26% of the variation in profit is explained by the variables in our model. R squared adjusted, a much fairer assessment after we penalize ourselves is about 71.61. Once again, that's just used to compare models, and that's actually not that bad. The RMSE is our model typically misses predicting profit by 0.274, so also not that bad. How many of the 10 interactions are statistically significant? Let's check it out. Going right here, 1, 2, 3, 4, 5, and 6. And this dot right here means almost. If you look at the codes for these, the dot is between 0.05 and 0.1. So anytime you see a star or something smaller, like star, stars, those are going to be statistically significant because these tell you the p-values between these values. So a dot would mean it's between 0.05 to 0.1. I don't know if it does if it's exactly, but you can oftentimes look for stars or multiple stars to tell statistical significance. Like that is statistically significant. That's almost. This is not statistically significant, nor is this or this right here. Or nope. So how many of those were statistically significant? 6 of them right there. Pursue use by running C interactions. So I did that right there with the many equal true. Yes. Report one pair, and there may be more than one pair of the variables that look to have a strong interaction. So do you think this interaction right here looks strong or weak, and why? So do you think this could be one we could report as a strong or more weak interaction? This one is between x4 and x5. Does it look to be strong or weak, and why? Like the x4, x5, and it's barely not statistically significant, which could give some hints if it's strong or weak. So this interaction could just be by random chance. Like what we're noticing right here between these lines. It looks weak right there. Great job right there, Peyton. And it's because the lines are more parallel. Same slope, exactly. Same slope, exactly, would mean parallel. With the stronger interactions, this is something going on here between x5 and x3. You also see it's more statistically significant. We could go to x2, x3 might have something going on. Something going on between x2 and x3. Look right here, difference in slopes, but x2, x5 is the real winner right here, and that one is the most statistically significant. Statistical significance is a good way to tell if there's probably something going on, and the weakest one is x3, x4 looks to be one of the weakest. Let's go look at that one. X3, x4 is this one. Yeah, this is the one we said that is like so not statistically significant because it's not statistically significant, and also the lines are about as parallel as line can get. It only if the p-value here was 1 would the estimate of the interaction be 0, and thus there would be no statistical significance at all. And it would be perfectly parallel. Fit a model predicting profit from x2 and x5 in their interaction. Visualize the model and take a look. Hey, that's what we just did. Let's just save as model. I always save what I do as model. And we're going to do profit tilde x2 times x5. This will also give us the x2, x5 term. And it's the product launch right there, data. And so we're going to summarize this. And there's our summary. We've got our model. Visualize it. And there we go. Definitely an interaction. And now we want to write out the implicit lines. This is where people usually get stuck. So the implicit lines are when we write out the equations for certain values. So what we want to do right here, which values are we writing them for? Well, we're going to write, let's write some implicit lines. The implicit lines that refer to the plot on the right when x5 is near 0 are the expected difference in profit between two products exactly. So let's do this. Let's write out an implicit line right here. Do we have enough decimals carried out? There it is. Ooh, I hate small numbers. I'm going to do the following, and this is very important. How to write implicit lines. Let me pause the video here and make a timestamp because I know a lot of people are going to ask, how do I write those implicit lines? So here's how we write implicit lines for values of x that we are inputting in. I am going to input a value of x2 of 6,000 and write the implicit line when x2 is 6,000. So now we need to write the model. I'm going to change my digits. So I think is it rounding? No. Digits equals 10. Oh, it's SciPen. Let's do that. Let's rerun our summary because I hate. There we go. Awesome. I'm going to go SciPen a little bit less. Sure. And then let's go digits. Doing this so I can actually see what the output is. That works fine. Okay. Here is how we write the model. We take our code right here and we need to write the equation. So let's start by taking our general form of y hat equals b0 plus b1 x1 plus b2 x2 plus b1 times b2, and then we have over here, oh my gosh, my brain's not working today, times x1 x2. Now, we have different things in here. This is a general form right here. I want to point this out. We are going to write the implicit line right now and plug in our numbers. So I've got the general form right here of the intercept, the first coefficient times the first x, the second coefficient times the second x, the third coefficient times x1, x2. What is, can anyone tell me just to 3 decimal places, what is the second coefficient in my model right now? What is the second coefficient? So it looks scarier than it is right now. Because we have right here, what is the second coefficient in my model? Take a moment, 100 points online right here. Just look at my output and tell me what's the second coefficient, not the intercept. What is B2 in my model right now? Not the intercept. Intercept is B0, which is, I mean, it's like, I don't know. What is B2, which is the coefficient of the second x in the model, which is not x2? Close. I'll take that right there. Close, Payne, you're close. That is going to go right here where B1 is. Does that make sense? That's going where B1 is. I'm going to round it down. That's where B1 is. Does that make sense? That is B1 because x2 is this x right here. Does that make sense? And then B0, we're just going to round this right here. B0 is this right here. Does that make sense that that's B0? We're predicting profit. And then we have x2. The second coefficient in the model is this. That's the second coefficient. This is the second x. I know they're named x. And then this is, just notice, wow, that's ridiculous. That's the next coefficient. We're going to round it up. And then it's x2, x5. Does this make sense what I've done right here? I've done, this is the intercept. And then we have here the first coefficient times the first x, the second coefficient times the second x, the third coefficient, and you could change this to a minus right here because it is minus. And there's the equation. It's good practice, especially if you have to write it out. So let's copy this and let's show the two things side by side from start to finish of what we had. So here it is before any changes. Is it going to change? Oh, I had one more change. Here's the general form of it. And then here is, what are you thinking, Peyton? How's it looking? And that should show. There we go. There's the output down below. And you notice right here, we have the name of the y variable right here, which is y hat, what we're predicting. B0 is the intercept value. B1 is the first coefficient right here to the first x, which is B2. B, which is x2. I love it, all that. And then B2 is the second coefficient of the second x, which the second x is x5. And B3 is the coefficient of the interaction term between x2 and x5. And that's our x1, x2 variable right here, which is x2, x5. If you notice the order, how's it looking? I just want to keep this on the screen so people can see how to write this. If you write out the general form and then you plug in the numbers, it should work. You just literally go this plus this times this plus this times this plus this times this. Does that make sense right there? And now what we're going to do to write out the implicit line is we're literally going to take this and we're going to solve it when x2 is equal to 6,000. So all we're doing right here is taking and plugging in this number right here. So we're going to take and plug in 6,000 for x2. This is how you solve an implicit line. It's just by plugging in the numbers. Because that's the interaction term. A good question right there, Peyton. That's the interaction term. The x2, x5 is the interaction term. So you see how this says, like the first and second term are x1 or x2 and x5 respectively. So the interaction term is the x2, x5 interaction term. So that's this right here is this right here. This colon right here means it's an interaction term, which means it's multiplied. Good questions right there, Peyton. With this question right here. This is probably one of the trickiest things, like if we ask on a test, but just with practice, just writing it out a few times, just write it down and then be like this plus this times this plus this times this plus this times this. And you just go through methodically. Intercept plus this times this plus this times this plus this times this. So it's always in order, like they're connected to each other and you just add the things together. So once again, add the things together. And then this question, like I'm making up a question, we are plugging in 6,000 right here because this says solve out the implicit line when x2 is equal to 6,000. Because that's what these lines over here are. So like 6,000 would be about a median value for x2. So we're solving probably for about this black line right here because this is when x2 is at a median value, which this is probably about the median value for x2. And we should get like a negative slope right here. So this line right here is when x2 is equal to about 6,000, let's say. So we're going to actually solve for the equation of this line right here, which is what this output does for us. So now we're just going to reduce down. Let's just take these values right here, and we're just going to multiply these two values. So that equals to this. That's minus this. We're going to take this right here and copy it one more time. And so this is equal to minus this times x5. And there we go. That's awesome. Love it. And then over here, this is just going to get added to the intercept. If you take a look at this value right here, this is just 1.8. And if you notice, the intercept on that black line is higher. The intercept on the black line is higher as x2 increases. And so now we're just going to add the 1.8 to this right here. And we get the new intercept of this right here. So let's add these. And now we just add these values, or rather we're going to subtract because these both have x5 in them. So we're just reducing down because these have like terms now. And we're going to subtract from it this. And we get a very slight negative line. And guess what? We have now just reduced this down. Oops. Did I took too much of it? Now we've reduced it down. So all we were doing right here was reducing. Does that make sense right here? We plugged in the value for 6,000. Let's look at the full process again. So we wrote out our general form. We plugged in the numbers from the output. Then we plugged in the value we're solving for. And then we just reduced down because this is all going to get added together. This is all a constant. This is something times x5. And then this is also something times x5 now. And guess what? We get an equation where we're predicting profit from x5. That's exactly what we see over here. This line right here is an equation where we're predicting profit from x5. Now, we might not have solved it out perfectly because we didn't carry all the decimals, but our number is close to 4. These were very, very small decimals. We do see around 4-ish with a negative slope. Also, we might not have plugged in exactly the median. So that's also probably part of the issue there too. But yeah, it hits around 4. Our line would be over here and go a little bit down. So it's probably a line in between here. Is this making sense right here, Peyton, how we can solve out for any of these lines or solve out for a line by plugging in a value for one of the two and then solving the equation so we only have the other variable in here still? So all we did is we wrote out the equation and then plug in a value of x2 to solve out the line for when x2 is equal to 6,000. So this equation right here is the equation predicting profit for a value of x2 of 6,000. So that's what we did right there. Awesome. Yes, this is a tougher topic. And I really like these activities because they give us more time to kind of talk about these things and for people to see the implicit lines. That's a tougher topic. We do put questions on the test on that. And so it's talking about all the implicit lines right there, which should be good. And the influence plot. Ooh, influence plot time. Are we doing it for the full interaction model? Finding outliers and flaws with even 5 predictions. Okay, we're going to use the full model right here. Are we doing it with an influence plot may fairly... on the interaction model. I want to make sure I use the right names for models. I think it's the interaction model. Good. Ooh, this is going to be interesting. Okay, let's go check it out. Here we go with an influence plot, and let's see what we get. Influence plot on the interaction model. Wait. Oh, I've got code running in the background. That can happen to you. Influence plot. Here we go. Awesome. I love it. So what is an influence plot? An influence plot is going to show us points that have undue influence on our model. There's 2 measures that kind of can lead to a point being influential. One, how far it is away on the mean of the x's, which is known as leverage, right? Below me right here, or right next to me is leverage. And so a point would have undue leverage, i.e. be too far out on the teeter-totter of our x's when it is beyond this amount of leverage. Now, this is not like a teeter-totter right here. Sometimes people get a little bit confused because when you're looking at this, if I draw it out right here, let me go draw it really quickly. Leverage is always a matter of degree from the mean of the x's. So the undue influence, if you have a regression model, points that have undue influence would be points that might be beyond here and here, because the mean of the x's is closer to here. When you make this plot, it actually takes, and anything close to here would have a leverage of 0 and folds this over. We're talking about burritos in class, not burritos, tacos and stuff, but it folds that over. That's what you're seeing is the folding over of this. Like fold this right here and fold it on top of itself. This right here is this right here. This is 0 leverage. Let me repeat. This right here is 0 leverage. This line you're seeing right here and right here, that's undue leverage, like things that are further out on that teeter-totter, and that's right here because it's been folded over on top of itself. And so we also have another metric right here, which is based on the y-axis, and this is going to be how much the model misses by, known as a deleted studentized residual. Now, please check out class for more details. We've gone over it very in depth. When you do a deleted studentized residual, you actually remove out the point's influence and then look at a model without that point. We might still have that up. Oh, you can load up. Got time series here. Yeah, go show it. Deleted studentized residual probably helps if I show it. When you have a deleted studentized residual, you remove out the point's influence and calculate the residual without the point's influence. Notice how this point's going to pull the line down towards it. So a deleted studentized residual would always be bigger than a residual because the line doesn't have the pull from the point. So you see right here, the deleted studentized residual would be right here. That would be the calculation, whatever that distance is from a line without that point's influence. You might be wondering, what does studentized mean? Well, studentized is basically the idea of standardized on a student t distribution. So anything outside of 2 or -2 is going to be extreme, and take a look. That's where those lines are at. So these points with these x's are the following points that have too much influence. Now it says leverage right here, but they have too much influence. The size of the circle on these plots are actually also the influence, and this is the most influential point. There can be points that are very influential but don't show up if they're like way over on the sides. Like that little one might not be as big as maybe that one. Like there's some that are, you see like that one's a little bit big. I mean, about the size of that. That point's really big but not marked because it didn't have enough deleted studentized residual. Very important to know that right there. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 influential points with too much influence. This is kind of the idea, especially in Stat 201, of QQ straight enough, no outliers. We don't want points with too much influence. We don't want outliers in our model. And these points have very extreme x values, which is going to be influential on the model. And they also have a far distance from the model itself when we delete it and standardize the distance. And that means they have undue influence, especially this point right behind me right there. Those all three of those points, but the one right above me didn't get marked because it didn't have enough deleted studentized residual. How many points were influential? Count them up right there. The point very far is 463. Well, let's go look at it. Let's go see what's so odd about it. Run the summary on the PL data frame for each of the columns. So let's go run the summary on the PL data frame. There's the summary. And extract the row. There's the row. And let's go take a look and learn about them. So here we are. Here's our summary. Oh, I want to get it all on one page. Let's see what makes them so influential right here. Good, I'm not blocking it. Their profit is 9,000, but that's not an X. We only care about their X's. Well, I mean, we'd have to look at the model predicts. But they have high leverage, I believe. Their X1 is 3, is that 3 million? Their X1 is 3 million, which is towards the max of X1. They have a very high X1 value. They're towards the max of X2. X3 is not that unusual. X4 is towards the maximum of that because they're very high in X1, they're very high in X2, they're very high in X4, and they're extremely low in X5. So that might be in a very unusual combination for deleted studentized residual Peyton. For deleted studentized residual, anything outside of -2 and 2 is unusual for deleted studentized residual. For deleted great answer right there, Peyton. And keep asking those questions if you have them. And then high leverage is calculated via the following equation right there. That's where that line was at in the plot, where it was on the x-axis. That line is this line right here. And then the -2 and 2 would be right there for the, awesome work. So I really think it's a combination of their X1 and X2 being extremely high and X5 being extremely low, and maybe X4 is pretty high. But that's probably why they're pretty odd right there. Next question. Check it out. Oh, are we doing polynomial? I love it. Love it. Polynomial models are some of my favorite topics. It's just because the output is so awesome and it's so cool to do and so pretty easy to get. So we're going to fit a linear model predicting profit from X2, and then we're going to run the choose order. So we're going to fit our model, LM, profit, tilde, and then X2, comma, data equals PL. And then we're going to run the choose order on it. Choose order is going to help us choose the polynomial degree order that we should use. And so if you're looking at this output, it kind of looks like a what. All these lines kind of look like a what. Take a moment right here. I'll let you think it over, because the answer we're going to derive from this is going to be that. All the lines kind of look like they're forming a what. Do you see it? We're going to figure out how to read this output here in a second. I'm going to put the steps, see if you can tell me what the right order is. So here are our steps, and make sure you do them in this order. A lot of people jump the steps. So with our steps right here, to find the correct polynomial order, here's what we do. Step 1, Find the highest R squared adjusted, because remember, it's the penalized R squared. If you add polynomial terms, the model will get better because you're adding more x's, like you have polynomial x's helping explain, so the model will have like more wiggle room to go through the data. You can go crazy right here and do something like max order 20, and then you get a bunch of craziness. Don't do that, though. Don't do that. Don't be like Brian. So right here, we can go and take a look. The highest R squared adjusted, I'm going to make it so it only appears out on the screen. The highest R squared adjusted is going to be this one. Step 2, take that highest R squared adjusted and remove off of it 0.005, not 0.05, 0.005. We're basically saying, like, yeah, that model's great, but could we maybe make it a little bit simpler? Like, we don't want to go to the 4th degree or 3rd degree polynomial. 3rd degree polynomial, which is this green line that's intertwined between all these other ones. So then we ask, and this, we're on step 3 now that we found our standard, which is we need at least this. That's what the standard means. So now we say, does this first one, is it more than this? Is this first one more than this? No. How about the second one? Let's see if you could do this, but for a different x. What is the correct polynomial order to use here? Ooh, that's a tricky one. Really? I might disagree with it. Is it? Ooh, it's a close one. If this was a test question, could you get it? What is the correct polynomial order? I don't love it. I might disagree with it. Peyton, 100 points, Peyton. You got it. So the highest is this. Step 1 complete. Step 2 complete. Is this higher? No. Is this higher? No. Is this higher? No. This is the answer. One more time, Peyton. See if you can do another one. Is this the one we just did? No, that's a different one, right? Which one would you use right here? Yeah, I might agree with this one. This one's so cool. They're basically 5 models that are identical. It wouldn't be 6 for this one. It wouldn't be 6. Let's go step 1. Which of these? So step 1, which of these has the highest R squared adjusted? Go through each step. Step 1, which of these has the highest R squared adjusted? First step right here. Just which of these has the highest R squared adjusted? This one's not meant to be a trick question. Good test questions right here. Good practice. Highest R squared adjusted right there. Just go through and be like, which one's the highest? And so now we have the highest. What we're going to do, we're going to subtract 0.05 from it. And this becomes our standard. Oh, no. Just take the highest R squared adjusted. And now we're doing this. We'll do another one after this to practice. And so this is our standard. Let me ask you, yes or no. Does this meet the standard? We're on step 3 right now. No, but so now we're finding out. So that is the highest, but we're not just choosing the highest. Remember, the first step is to find the highest. Then you subtract 0.05, and then you go and find the one starting from the bottom that passes the standard first. So here we're on step 3 right now. We'll do the step-by-steps again here in a second. Does this one meet the standard down here? Yes or no? We're on step 3. Does this meet the standard? Yes or no? Is that higher than the standard? Yes or no? Is this right here higher than the standard? It won't be 2. Is 2 higher than the standard? Because you'll start from the bottom and say no. I'll let you see. Do you see which one it is? So do you see which one is the first one to meet the standard, which goes over the standard we have? And I'll do a different one, see if you can get it. You got a good practice. It is 4. Great job, Peyton, right there. 100 points. This is our thinking music. We haven't played this in forever. It is 4. Because 4 is the first one past standard. Let's do a different one right here. Just practice. Make sure we can get this down. There's no 6. Okay. Can you get it? Step 1, find the highest R squared adjusted. Step 2, subtract 0.05 from it. And then step 3, find the one that meets the standard first. Which one will it be? Which one shall we choose? Step 1, find the highest R-squared adjusted. Step 2, subtract 0.005. Step 3. Well, but 0.005, 0.005, 0.005. A lot of people do 0.05. Don't do that. Because we're not doing like statistical significance subtraction from it. We're doing like a very small little tiny takeoff of it because we're choosing something very close to it that is basically as good as it. Basically. But we want something simpler, something that's not as complex as like a fifth order. So the fifth order was the best. But what is just paid another 100 points? Yep, it's 4 again. Does not meet it, does not meet it, does not meet it. Does meet it. Good job right there. Hey, Sakia, good to see you here. I miss you too. Good to see you here in the chat. Awesome. I love when former students swing by. Awesome. Fit the model predicting profit with all the interactions, including the relevant polynomial term right here. So let's include it. Fit the model predicting profit with all interactions, including the relevant polynomial term in X2 in the PL data frame. Take a look at the summary. Okay, so we use the poly function. LM, profit, all two interactions, and a polynomial. Profit, all two interactions, plus poly, x2, there we go, and degree equals 1. I can just put that right there. Data equals... Hope your semester's going well, Sakia. Yes, it worked. We love that. Did the polynomial bring with it new information? There's the poly. Ooh. Oh, because it already has this. The reason right here that it's giving NAs is because X2 is already in the model. This is the polynomial of the first degree right here. And the polynomial is actually helping. Wow. It's pretty cool. So the polynomial is bringing with it new information as we see by the low p-value. The reason these are NAs is because this is X2, so it can't add X2 to the model twice. So... that's perfectly fine. I might be able to fix that up. I wonder if this will fix the output. Nope, still doing that. Let me see if I can do like a not carry model hierarchy. Poly. Coefficients raw, simple, false. What does simple do? Whoa. What does simple do? And whenever you're wondering about a function, run it. Over here, take a look. Logical indicator if it's simple matrix, no. Degree, well, we already know what degree is. I want to not carry through model hierarchy, but maybe I won't do that. Too bad. We get the output that looks like this. It's all right. It just means that it already put it in the model. It can't estimate coefficients for something that's already in the model. Is the highest order of the polynomial statistically significant? Mm-hmm. And we're only putting into the second degree, right? Or were we putting into a higher degree? Let me take a look at that again, because I can't remember if we had the second going to a higher degree. Oh, we do. We have it going to the third degree polynomial, because this is the highest. Subtract 0.005. Oh, no, we're only going to the second. Okay, good. We're only going to the second degree polynomial. So we're good right there. It was the second. And it is statistically significant. We do see that. Has the model improved from our previous terms? Okay, let's go take a look. We need to do some model comparison right here. And nope. Here's our model now. That's not right. There's our model now. And let's look at the model with the interactions only. And I think we can get the R squared out of this. Let me go right here and go msum dot int. Because I think we can go to these and get the msum. Watch this. Here's a trick. And let's get the R squared. There's the R squared of the first model. And here's the R squared of the other model. And so, yeah, it has gone up. But we probably want to look at the R squared adjusted. And adjusted R squared right here. So here's our previous one. And here's our new one. Oh, it's gone up? Well, I'll be. Very good right there. We can probably grab the RMSE. RSE? Residuals? Well, we'd have to calculate the residuals doing this. Much better ways to look at our original model right here And looking at the original model, it had a typical miss of 0.274, and our new model has a typical miss of 0.268. A change that's very small but worth it, and we are seeing the R-squared adjusted go up. Here's the old R-squared adjusted of 0.716. Here's the new R-squared adjusted of 0.729. Seems to me like this is a good idea. Seems to me like this was a decent idea right here. Pretty good idea right there to add in the polynomial term. Actually increases model metrics. I do want to point something out. What am I doing right here? I'm comparing two models. I'm comparing the models on their residual standard error, which is the typical misses the model make, and also I'm looking at an R-squared adjusted because these are multiple models. So these right here are your model comparison metrics when you're looking at multiple models to say, well, which model's the best? Well, let's look at the typical misses they make. Let's look at a fair metric to compare models with multiple variables. Good stuff right there. Let's do some variable creation. So we're going to create some new variables right here with x3 and x1, and let's do it. So we got right here the idea of variable creation, which we've gone over. And we're going to take x1 and divide it by x3 plus x5 to see if it makes a new variable of interest. So to do this, we need to take, and I'll show you, let's do a trick. If you attach a data frame, the vectors become available in the global environment. So attaching the data frame makes it right here so I could call x3 and x3 appears. Only because I've attached it. If you don't attach it, you have to call it via environment, and that's where you run into errors. Let's see if this fixes it. There we go. I think I already had like an x1 or x2 or something stored in the global environment, so that was causing issues. So watch out. You could always take and run this by doing PL $x1 divided by PL $x2, all that stuff right there. And so now we're going to take the PL data frame and we're going to store PPA as variable PPA. Now you might be asking, why didn't we just do it in one step? And the answer is we very well could have. All we're doing is appending on to the PL data set a new variable created. So this right here creates it. I a lot of times like to create it in two steps where I create the variable and then I append it onto the data frame. If you store into a spot that does not exist, it creates it onto the data frame. Code fitting a model right here. To fit the model using it, we're going to run right here profit, which is capital P, tilde PPA, new variable in the data frame, data equals, and the PL data frame. There's our model, and let's look at how this model does. Woo! How's this model do? Not good. Not good. That's not the model right there over on the right. The model is this. Not good. Not good model. That PPA variable did not do a good job. The model typically misses by about 0.51, which is much larger than our typical misses on other models. Only explains about 2% of the variation. R-squared adjusted is not that bad, but it's a one variable model. Overall, this model is not that good and probably is going to fail our check regressions because it's got outliers. Name opt is missing. Oh, check options. And it actually passes the linearity. Linearity is good. Normality of residuals is bad, but not that bad. It actually does okay on conditions. Equal spread is bad, but it's a bad model. So even if it passes those conditions, it's like, well, that's not that good. Last but not least, right here, we're doing some predictions with extrapolation to see, well, checking to see if things would be extrapolated. So let's talk about some extrapolation right here and how the extrapolation check function works. So the way extrapolation check function works is actually very complex. If you've taken any sort of linear algebra, you might have heard the terms like eigenvectors, eigenspace. We're concerned about a multi-dimensional X space right here, and I'm only drawing a 2X space, even though we're higher dimensionality than this. Like we could have like a third X dimension right here, and notice there are no Y's. Because when we extrapolate, we're going to extreme values of the X's. Now, I'm not good at drawing 3D drawings, so I'm only going to go down to a hypothetical 2D X space. So if we had our X variables like this right here, we'd ask how extreme is a certain point on its value of X's. So we'd go inside of here and say, is this extreme? Is this extreme? Is this extreme? Let's do different colors right here and talk about them real briefly. Now, the most extreme point on here would be something in the pink area, even though that's about the same equidistance from the mean of the X's as the yellow dot. maybe it's a little bit further, but not too much. What we're actually concerned about is what are called eigenvectors and eigenvalues. We will not be calculating these. But if we bring this down to an orthogonal space, you'll notice right here that the extremeness on this orthogonal space, which is a 90-degree space, is more extreme for this point right here than the yellow point. The yellow point is way less extreme when we talk about like the spread in these orthogonal spaces. So there's some pretty complex mathematics being done right here. But probably one of the best ways to think about it is kind of a density ellipse radiating out right here and when it would hit these points. How far out from the center would you have to go? And the answer is for this point right here, 100%. For this first point in the very center, it's at the center, so it's at the 0th percentile. This point right here might be at something like the 60th percentile, as in we'd have to go through 60% of the data to get to it. And that's what the extrapolation check is doing when it returns a number. So if a number like 0 or 10 or 20 is returned, the point is very close to the mean of the x's. Not much extrapolation would be required to make the predictions. Or if it's towards like 50, 60, 70, 80, then it's towards an outer edge. If it's like 90, 95, 100, then something crazy is going on. Especially if it's 100, then it's beyond the outer edges of our x variables. And once again, this is in a multivariate x space, so we could look at something with more than just 2 x's. We could look at all of our x's right here. Now, how many of these are we predicting? How many new x's are we predicting? We're predicting 2 new x's. And you'll notice right here we have x1 has values either 80,000 or 2 million about. X2 has values either 3,000 or 9,000. And if you look at the data frame, it might be easier for you to see that we're just making a data frame called toPredict, where we have one row for an x1, x2, x3, x4, x5 combination, and another row right here for an individual with all these x values. So there's our first individual, second individual. The way it looks in the code is first individual's x1, first individual's x2, and you go down here, and this would be the second individual. It kind of takes it and turns it into the column in the data frame. And so let's run the extrapolation check right here, given to you right there. Person 1 is where we'd be extrapolating. Person 2 is not towards the mean of the x's because they're at 56.7. They're 56.7% of the way through the data. They're about like this person over here. They're towards when you radiate out through the x's. So this person right here, this person 1 right here, is a very extreme combination. So they would require some sort of extrapolation, which means more uncertainty in their predictions. And it's kind of like, should we be doing this? Is this a good idea? Because when you extrapolate, your model is predicting on values that are far away from a model that is reliable and a good reflection of what you should be predicting. Well, I think that's got it. Great job here, everybody. If you have questions, let me put on a little music, hop back to the main screen. Those are the topics in multiple regression right here. Make sure to review them and ask questions if you have them. Know how the code works. Know what the output's showing you. That's very important. Like, we just got a few numbers right there, but what do those numbers mean? The biggest thing we have to ask is when we get output, what does that output mean to us? And with that, everybody, it's the end of the activity. Great job, Peyton, everybody who's here, following along. I'm sure some people are going to watch this later. I love the videos get tons of watch. It means a lot to me that people use these to review. With that, we're done. I'll see you later. Bye for now. Bye.